Hi, everybody. Welcome. My name is Angela Jensvold, and today we are going to review two-dimensional kinematics. We're going to start with a warm-up. I'd like you to find the horizontal and vertical components of this velocity vector. I'm going to give you 30 seconds. Okay, so what we want to get is the horizontal component of velocity and the vertical component of velocity. Okay, so the sine of an angle, if you know SOHCAHTOA, it's opposite over hypotenuse. And the opposite side for us, here's our angle 30 degrees. The opposite side is the vertical component of the velocity. So if we solve that, this is really Vy over the hypotenuse, V. So if you solve for Vy, you get V sine theta. So this would be 5 meters per second times the sine of 30 degrees, which is 2.5 meters per second, because the sine of 30 is 1/2. Okay, and then if you remember from SOHCAHTOA, cosine of an angle is adjacent over hypotenuse. So our adjacent side is the horizontal component of the velocity, Vx. Okay, so if you solve for Vx, you get V cosine theta, which is 5 meters per second times the cosine of 30 degrees. Trying to erase that mess. And if you plug that in, you should get 4.33 meters per second. So those are the components of our velocity vector. I hope you guys were able to get that. All right, so today, what are we going to do? We're going to do only one learning objective, change 2.8. These are from the course and exam description. The AP exam is written according to the learning objectives. If it's not a learning objective, it's not going to be on the exam. So when we review, I'm going to be hitting on learning objectives to make sure you know how to do all the stuff that's on the list, okay? So today it's only one learning objective, but there's a lot to it. So what does it say? Calculate components of velocity. You just did that, so mission accomplished. You should be able to do the same thing for position and acceleration in 2 dimensions. Calculate a net displacement of an object moving in 2 dimensions. Calculate a net change in velocity of an object moving in 2 dimensions. Get average acceleration, and then describe velocity vector for an object moving relative to another object with respect to its frame of reference. What does that mean? That's relative velocity. So we're going to look at that today. Okay, so one particular common type of 2-dimensional motion is projectile motion. Projectile motion is an object that's usually launched. It's under the influence of gravity only. You neglect air resistance for projectile motion. So what you need to know is that the horizontal acceleration is 0. In order to have an acceleration, you need a force, and there's no force in the horizontal direction to change a baseball's state of motion. The vertical acceleration is negative g. Why is it negative? Because the Earth is pulling down. The convention is normally that up is positive. Negative g. Horizontal, this is like the core understanding of projectile motion, okay? Horizontal and vertical motions don't affect one another. So what you need to do, the strategy you need to use when you solve projectile motion problems, separate it out into X and Y. So take the horizontal motion, analyze that and find what you can. Get the vertical motion, analyze that separately and find what you can. And then you can put the two together, the two pieces of information together to look at a complete picture of the motion of the object. Okay, that's what we're going to do today. What I did here below is I just took our 3 kinematic equations that Mr. Frensley went over, and I just added a couple of subscripts, x and y subscripts. So the first equation is for the x direction, but what did I just say? Horizontal acceleration is 0. So couldn't we just get rid of this term? So really, horizontal position is just wherever you started off at, plus the rate at which you're moving times time. It's kind of like distance equals rate times time, if you're familiar with that. Okay, and then on the equation sheet, it's x equals x naught plus v naught t plus 1/2 at squared, but I change it to y when I'm doing vertical, just to be clear. And then instead of a, I plugged in negative g. Acceleration in the vertical is negative g. So I plugged in negative g for a, and I got that second equation. Okay, the next one, Vx is V naught x plus axt, but ax is 0. So really what this says is that Vx is equal to V naught x. Okay, that's an equation, but what does it mean? It means that the horizontal velocity at any time is equal to the initial horizontal velocity. In other words, the horizontal velocity doesn't change. Why not? Because it's not accelerating. Why isn't it accelerating? Because there's no force changing its motion horizontally. Okay, and then for the next equation, Vy, I used V equals V naught plus AT, but I put a Y subscript on it to specify clearly we're isolating the vertical motion. Okay, what is the acceleration in the vertical? Negative G, so I just plug that in. Okay, the next one is another horizontal one. Oh geez, AX is 0, right? So if we rewrite this equation, it says Vx squared is equal to V naught x squared. What does that equation mean? That means that, well, you know what? If we just square both sides, we would get Vx is equal to V naught x. We knew that. All that means is that the horizontal velocity does not change. That's all. And then the last one, I substituted a negative g in for the acceleration. Okay, we're going to use these now to solve some problems. Okay, the first one, I just took a bunch of problems from AP Classroom that, most of them are from AP Classroom, that were tied to this learning objective that we're doing today. And I might have modified them a little bit, but essentially, this is what you need to know, okay, for this particular learning objective. So this is some kind of a trebuchet. It's launching an object, and it launches an object horizontally at the peak, and it's launched at a speed of 5 meters per second, perfectly horizontally. Please find the velocity at impact with the ground, okay? See if you can do it. I'll give you 1 minute. Okay, how'd you guys do? All right, we were trying to find the velocity. So I didn't say speed, I said velocity. So you need to give me the vector. So maybe the easiest way is unit vector notation. So here's what we know. Vx at any time is equal to V naught x. Well, that's 5 meters per second, and we'll put the unit vector on there. Okay, so we're done with the x component. That was easy. Now the y component is V naught y minus gt. I'm getting these equations from the slide before. So if you need to go back and refer to them. What is V naught y? Well, this thing was launched horizontally. So the initial y component of velocity is 0. So It's just negative 10 meters per second squared times t. Oh, we don't know how long this thing was in the air. But if you look at the picture closely, you can see that it started at a height of 15 meters. So why don't we use an equation that has height in it? So I'm going to use this one, y equals y naught. Here's the deal. How do you know which equation to use, right? That's sometimes what my students ask me. How do we know to use this one? Well, I know because I've been doing projectile motion problems for decades. But how would you know? You might not know. But there's three main equations, right? So if you choose the first one, I'll just scribble down here for a minute. Let's try this one. V naught plus AT. Okay, it has time in it. We know we're looking for the time in the y, let's say. We know the acceleration, the y, but we don't know the final vertical component velocity. So we've just reached a dead end. That's okay. We learned something. We've gained experience. So we're going to erase this. We're going to erase this. We're going to try another equation. Let's try Vy squared equals V naught y squared minus 2g delta y. That one has height in it, and we know the height. It's 15, right? Or the vertical displacement is a negative 15, so we can plug in negative 15 for delta y, right? We know g. Actually, we could have done this from the beginning. I'm really glad I did this because I was doing it in a roundabout way when there was an easier way to do it. So do you guys should we just take the easy way? Let's just do it this way. So V naught y is 0. I'm so glad I did that. So Vy, when it hits the ground, is going to be the square root of negative 2 10 meters per second squared. What did we say delta y is? Y final, 0 meters, minus y initial, 15 meters. Okay, and then you get Vy is, I solved it earlier, so I can tell you, negative 17.3. Why is it negative? Why is this? Does this make sense? Remember, we were trying to get into the practice of looking at our answers and seeing if it makes physical sense. So why is the vertical component of velocity negative? Because it's going down. It might be going sideways at the same time, but it's also going down. So negative 17.3 meters per second. Okay, so all this business up here, what was I trying to do up here? We could have gotten there. It's not wrong. What we were doing up here is not wrong. It's just a different way to do it. It might be a little bit longer than just using this one equation in a more straightforward manner. It doesn't matter. As long as you we're going to end up in the same place. Okay, so I'm glad this happened. Okay, so let's write our final answer here. Okay, the question is find V final. V final is 5I minus 17.3 J meters per second. How about that? Okay, so there's multiple ways to do a physics problem. I don't want to say there's no wrong. There's many wrong ways to do it, but there's multiple correct ways to do a physics problem. There are easier ways to do it, but don't worry about it if you took the longer path. Okay, now we have a question. We are given this object starts from rest at the origin, which makes things easy. You have the components of the acceleration, and you need to find the net displacement when the vertical coordinate is 12 meters. Give it a shot. Okay, I hope you guys were able to get it. Your 1 minute is up, or at least you got a good start on the problem. In order to find the net displacement, we need to get the x and y coordinate. We already have the y coordinate, it's 12. So we need to get the x coordinate. X equals, you know what I want to do actually is because we want to look at the, okay, let's see. So x is equal to x naught plus v naught xt plus 1/2 axt squared. Oh, but it started at the origin, so x naught is 0. It started at rest, so v naught x is 0. So basically, to get the x coordinate, we need the acceleration in the x direction and the time. We've got the acceleration in the x direction, but we don't have the time. How can we get the time? We can use the fact that it's at 12 meters. So let's use this equation, v naught y t minus or plus 1/2 a y t squared. Why aren't I using minus 1/2 g? Because this is not a projectile. The acceleration in the y is 1. So it's tempting because we have so many projectile problems to plug in negative g for a, but make sure you're thinking about the scenario before you do that. Okay, for this object, it starts at the origin, so y naught is 0. This object starts at rest, so v naught y is 0. So we can solve for time. Time is 2y over acceleration in the y square rooted. It went 12 meters, so that's 2 times 12 meters over acceleration in the y. So you get square root of 24, which is 4.9 seconds. Okay, now we have the time. So we separated it out, right? We separated the x, we're analyzing that motion, we reached a dead end. So then we went over to the y, we're analyzing that motion separately, and we're going to use that piece of information to go back and complete the picture. So let's plug it in. X equals 1/2 2 meters per second squared times the time, 4.9 seconds squared. And for x, you should get 24. Oh yeah, because it was the square root of 24. 24 meters. Okay, so if you want to find the net displacement, you could say delta D. It moved 24 meters in the horizontal direction, and it moved 12 meters in the vertical direction. Don't forget your units when you're done. Meters, right, for displacement? Okay. All right, so now you have a ball that was thrown. This is a projectile. I want you to find the net change in velocity from 0 to t, the change in velocity. Okay, so I hope you guys did change in velocity is the final minus initial. So first you need to get the initial velocity. The initial velocity, okay, maybe we should draw a picture here. So you have a ball, it's thrown with a speed v naught at an angle theta, okay? So there's our sketch of the situation. V initial would be v naught cosine theta in the horizontal direction, and v naught sine theta in the vertical direction. Okay, that's our v naught vector. Now later on, what is the horizontal component of velocity going to be? Well, we said acceleration in the horizontal is 0, so it's just going to be the same. V naught cosine theta I plus, okay, Vy. We're going to use this equation, Vy equals V naught y minus GT. We've got V naught y here. Maybe I'll put a bracket here. V naught sine theta minus GT. And all of that is in meters per second. So that's your final velocity. So now what we need to do is we need to subtract these two vectors. So we need to take this vector, the initial vector minus the final minus the initial actually, right? So let me get rid of that. So I'll put the negative here. Okay, so if we take V naught cosine theta I minus V naught cosine theta I, we get nothing. Okay, so delta V is 0I. And then if we take V naught sine theta minus GT minus V naught sine theta, we just get minus GT. That should have been a J. Meters per second. That is the change in velocity. Okay, you just subtract the initial and the final velocity vectors. Okay, so now we have an object starts at rest from the origin. You were given both components of the acceleration, and then at time t, it has a displacement delta d1 and a velocity v1, the magnitudes, okay? Then they take the same object, put it back in the origin, they double both components of the acceleration, and then at time t, it has a displacement, a magnitude of displacement delta d2 and a magnitude of velocity v2. You need to compare the two displacements, delta d1 and delta d2. So you're going to have to find the acceleration vector, the average acceleration vector in order to do that. So give it a shot. Okay, I know you guys might not like doing problems in all variables, but that's what we're going to do because a lot of times on the AP exam, it's just variables. It's not numbers. So we have to practice. Okay, so we're trying to compare the displacements, right? I'm going to call this situation 1 and I'm going to call this situation 2. Okay, so if we want to get the displacement, delta D1, we would have to do the thing is it starts at the origin, so we'd be subtracting 0. So we basically just need to find the final position, okay? The distance that it went, basically. Well, just write it out. It would be 1/2 AT squared because it starts at the origin and it starts at rest. So the V naught term is 0, the D naught term is 0, so you just get 1/2 AT squared. Okay, but what is the acceleration? The acceleration is in two directions, right? So the magnitude of the acceleration would be square root of A squared plus A squared, and that is the square root of 2 times A. Okay, so we're going to plug in the square root of 2 times A t squared. Okay, that is our delta D1. Now, let's do it for the second situation. Okay, so that was A1. So let's get A2 would be the square root of 2a squared plus 2a squared, which would be 4a squared plus 4a squared. Square root of 8 is 2 square root of 2a, right? So for delta D2, you get 1/2 of 2 square root of 2a t squared. Oh, okay. Well, if I take delta D2 over delta D1, I get 2. So what that means is delta D2 is equal to twice delta D1. Okay, now we want to relate their velocities. Okay, let's give it a shot. Let's do V1 would equal V01 plus A1t. But V0 is 0, right? It starts at rest. So A1 is the square root of 2a t. And now let's do it for V2. V2 is V02 plus A2t. But V02, it started at rest at the origin, so it's 0. So you get 2 square root of 2a t. Now, once again, if you take V2 over V1, we get 2. So that means that V2 is equal to 2V1. Okay, great. Okay, here's where the relative velocity comes in. This is not a calculation. This is more about drawing a sketch. I want to help you get started on this one in case you don't remember relative velocity. So I will just tell you that we're trying to get the velocity of the cyclist relative to the train. Okay, so whenever you do relative velocity, they gave us the velocity of the cyclist relative to the ground, right? They gave that to us. We want to add that to the velocity of the ground relative to the train. Whenever you do relative velocities, you want these inner subscripts to match, and you want the outer subscripts to be what you're looking for. We're looking for the velocity of the cyclist relative to the train. Okay, please try that. I'll give you a minute to do it. Okay, I hope you noticed that this vector they gave you is really the velocity of the cyclist relative to the ground. And this one is the velocity of the train relative to the ground. But in our equation, we want the ground relative to the train. So imagine you were in the train. Wouldn't you see the ground moving west at this same speed? This is the velocity of the ground relative to the train. And we want to add those two vectors together. So if I draw them over here, it would be velocity of the cyclist relative to the ground. Now when you add vectors, you put them head to tail, right? Add this vector, velocity of the ground relative to the train. And then our resultant vector is this one, the velocity of the cyclist relative to the train. So how would you describe that vector? I would say that it's north of west. Okay. Why don't you guys try this one? This looks like an old AP exam problem just from the diagram. You're launching something horizontally off a building. It lands 3 meters from the edge. Find the horizontal component of velocity. Give it a shot. Okay, so you want to find out the launch speed of this thing. So if we want to find Vx, Vx would be the horizontal displacement divided by time, right? And we know that it goes 3 meters horizontally, but we don't know how long it takes. So why don't we go to the y direction to find the time? So I guess we'll do y equals y naught plus v naught y t minus 1/2 gt squared. Okay, it lands on the ground. So y would be 0. Why not? We know that it starts with no vertical velocity, so this would be 0. So y naught minus 1/2 gt squared. So let's solve for time. You get 2y naught over g square rooted. So the height is 10 meters. G is 10 meters per second squared. So your time is 1.414 seconds. Okay, so now we use the y motion to get the time. Now let's take the time and plug it back into the x to get the launch speed. So it'd be 3 meters divided by 1.414 seconds. And you should get 2.12 meters per second. Okay. Okay, this one's more of a sketch, not as calculation based as the other one we just did. So make sure you draw a sketch. I think you can definitely do this in a minute. Okay, how'd you guys do? There's a circular path, right? And let's say this is the beginning of the path, I guess. All right, so we have person X walked halfway around. So from here to here, displacement is just from where you started to where you ended. So the magnitude of that displacement should be 100 meters because the circle has a radius of 100 meters. Okay, what about person Y? They walk 3/4 the way. So I'm going to start at the same place, go counterclockwise. Doesn't matter if you go clockwise or counterclockwise, you're going to get the same answer. So that displacement is this big. I'm not going to calculate it because we're just doing a ranking. Okay, so let's see if we can get away with not calculating it. Then we'll have person Z goes all the way around. If you go all the way around, your displacement is 0 because you started and ended at the same place. So delta dz is 0, right? This red one is delta. Whoa. I think I just lost control of my pen there. D1 is 100. And then the green one, it's not 1, it's X. There we go. And then the green one is delta dy. Okay, you can just look at the picture and you can tell that delta dx is bigger than delta dy. So I'm not going to calculate. I could, right? Because I know this distance is 50 meters and this side of the triangle is 50 meters. I'm not going to waste my time because I can already, they just want us to rank them. So I'm going to say delta dx is bigger than delta dy, and that's bigger than delta dz. Done. Easy. Okay, so I'm giving you the components of a ball's velocity and acceleration. It's not a projectile. Describe the velocity and acceleration at 2 seconds. Okay, so you want the velocity vector at 2 seconds. So the velocity at 2 seconds would be 5I. And if I plug 2 seconds into Vy, I'll get 3 times 2 minus 6, which is 0, right? So that's just 5I meters per second. That's your velocity vector at 2 seconds. Now the acceleration vector would be 2 minus 7. It's not a 7. I plus 4 times 2, 8 minus 2, J meters per second squared. So 2 minus 7 is negative 5. 8 minus 2 is positive 6, J meters per second squared. Now it says describe the vectors. So if I was going to look at this object, the velocity at 2 seconds is 5I meters per second. That means it's moving horizontally in the positive direction. So let's say it's moving to the right, okay? And then the acceleration, interesting. The acceleration, the horizontal component of the acceleration is negative. So if it's moving in the positive direction, but the acceleration is negative, that means it's going to slow down. So this object is slowing down in the horizontal direction, and it's currently not moving vertically, but it's gaining speed in the vertical direction. It will be moving upward in a moment. So it's nice if you can go back and forth between these representations, like a equation, graph, narrative. Okay, let's do a little calculus, just a tiny bit. I gave you the coordinates of an object, find the components of the velocity at 0, acceleration at 0, and then write expressions for position, velocity, and acceleration at any time. Okay, so to find velocity, I hope you took the derivative. So the derivative of sine is cosine. So negative 50 cosine omega t I. And then the derivative of the y component, the derivative of 40 is 0. And the derivative of cosine is negative sine, so it becomes a positive 50 omega, I forgot an omega over there, sine omega t. Oh, could I squeeze in an omega? I think I have room. If I erase this negative, put a tiny little negative and an omega there. Okay, great, saved. Okay, so that's your, this is your velocity at any time. Okay, so we're kind of, I guess we're going a little bit backwards. We're doing the third part, write expressions for the velocity at any time. So the velocity at 0, if you plug in 0, cosine of 0 is 1. So you get negative 50 omega I. Sine of 0 is 0. So it's just, that's it. That's the velocity at 0. And then we want to find the acceleration. Acceleration is the derivative of the velocity. So we differentiate the expression we got for velocity, and the derivative of cosine is negative sine, so it'd be negative 50 omega squared sine omega t I. Derivative of sine is cosine, so that would be plus 50 omega squared cosine omega t j. So this is the expression for the acceleration at any time. But if we want the acceleration at 0, sine is 0, so it would be 50 omega squared j meters per second squared. Yeah, okay. Honestly, the position vector, we could just do it here. They pretty much gave it to us. Negative 50 sine omega t plus I plus 40 minus 50 cosine omega t j. Okay? It's not so bad. All right, let's just make sure you got it. I'm going to have to do this with you. If you're watching this later, just pause it and try to do it yourself because you should be able to. But since we're running out of time, I'll do this for you. Let's just draw a picture. You have a rock thrown horizontally off a cliff, and the height is 50 meters. Find the initial position vector. Well, if I call this x equals 0, then it would be 0i plus 50j meters. Find v initial vector. V initial is 10i meters per second plus 0 because it's not moving vertically. Okay, Vx as a function of time, honestly, it's just 10 meters per second because there's no acceleration in the x direction. This is a projectile. There's no force changing its state of motion. Vy as a function of time is a little bit more interesting. It'd be v naught y minus gt, and v naught y is 0, so it's just minus gt. There's your function for the vertical component of velocity. Now, if you want to get an equation for the horizontal position at any time, you would use x naught plus v naught xt plus 1/2 ax t squared. But ax is 0. This is 0. X naught is 0. So you just get 10t. There's your function for the horizontal position. The vertical position would be y naught plus v naught y t minus 1/2 gt squared, except v naught y is 0. So you would get 50 minus, I'm going to plug in 10 for g. Half of 10 is 5, so I'm just going to write 5t squared. I know I'm going a little fast, I'm sorry. All right, how long does it take to land? Well, heck, why don't we just use the equation that we just found and set it equal to 0? Wouldn't that work? Solve that for time, and it'd be the square root of 50 over 5, the square root of 10. What is that? That is 3.19 seconds. Okay, and then the velocity when it lands. So we can plug our time back up here, negative 31.9 meters per second. I took g, which is 10, multiplied by the time, 3.19, I got 31.9. And we know Vx is always 10. So V final would be 10I minus 31.9 J meters per second. Why is that Y component negative? Because it's going down. Why is the X component positive? Because it's still moving to the right. Okay? Okay, so just to summarize, for projectile motion, horizontal acceleration is 0, vertical acceleration is negative g. The horizontal and vertical motions don't affect one another, so you separate it out, analyze the x separately, analyze the y separately, put the information together to get a complete picture of the motion of the object. I have our simplified equations that we derive together. And I'm going to leave you with this homework. This homework is due on Monday. So Mr. Friendly is going to be here tomorrow, and then we'll pick up with two-dimensional motion again on Monday, okay? So this is your goal to complete for Monday. Thanks for watching, everybody. Stay home and stay safe.